Hello and welcome back. This is the second part of our lesson on refraction, and here is where the rubber meets the road. We are going to talk about lenses, because one of the great uses of refraction is we can use lenses to change the path of light in really specific ways depending on what we want them to do. You could think about eyeglasses for correcting your vision, or using it in a microscope to zoom in on objects. Now, lenses are going to work kind of similar to, but somewhat different from, our idea of curved mirrors. You can recall that when we looked at a converging mirror, it had a focal point and it caused all the rays to kind of converge to a point, and by looking at how those rays converge, we could figure out what the image is going to look like. And we had to only look at two rays, and then we could have a third one to kind of check just to see what our image should look like. And depending on the position, our image might be real or it might be virtual. It might be larger, smaller, inverted, upright, and all those things. So the same thing is true for lenses. You can imagine that if I've got, in this case, this is a converging lens. So you can see that if I have many rays coming off of this object, that the rays that go through the lens tend to converge together. So it's a converging lens. And so again, if I just pick a few specific rays, I'm going to pick these specific rays, I can see where my image is going to be, and depending if I'm closer or further away, that changes my image. It's upright, it's inverted, it's virtual, it's real, and so on. And so we want to be able to understand how that works. One thing to note that is that you can see that these rays don't even hit the lens. Because this is geometric optics, we can just think about what the lines are doing. And what I mean is the lens itself, you can imagine that it's very, very, very thin, and that it's very, very tall. So you can just draw a straight line up and down that kind of represents the lens, and any line that hits that is going to bend. So again, there's going to be different situations depending on where we put our object. Now, again, this is a converging lens, and you know it's a converging lens. That is true for any lens that is wider in the middle than it is towards the edges. So you might look at that and think, oh, that kind of looks convex, and you wouldn't be wrong, but I would stay away from that terminology, because a convex mirror and a convex lens do different things. And so I would think of them as being either converging or diverging. It's just going to be harder to mess that up. Okay, so because this is the converging lens, it's going to have a focal point kind of on the back side of the lens. And so take your ruler, and it doesn't matter too much where you draw your focal point. Just make sure you have some defined distance for your focal point. And then also on the other side of the lens, the same distance away, I'm going to draw another point here, which will be important. And I'm going to label this as F prime. It's sort of the virtual focal point. The light is going to get converged on the other side of the lens, but this is going to be an important point, as we'll see in a second. And just a reminder that this lens, you can just imagine that this lens extends in both directions kind of forever and ever. So if we run out of lens, if we don't hit that exact curvy lens, that's fine, because that line will represent our lens. Okay, so I'm going to start with an object here, and I'm going to start with an object beyond F. So over here somewhere, I'm going to draw a nice simple arrow, because it's within my artistic ability to do so. All right, so just like before, we want to figure out where the image is and what it's going to look like. So we only really need to draw two lines in order to do that, two rays. So the first ray is going to be familiar to you. That's going to be a ray that goes from the top of the object and goes parallel to the principal axis until we strike the lens. And so if I line up my ruler, I get something sort of like this. Okay, very nice. All right. Okay, so if that ray goes parallel to the principal axis, then when it refracts through the lens, it's going to bend and go through the focal point. So if I line up my ruler with the focal point, and I'm going to draw that line kind of as far as I can, you can see that the ray is going to travel parallel to the principal axis and then refract through the focal point. Okay, so I need another ray, and then where those two meet will tell me some information about the image. So the second ray that I'm going to draw is not necessarily immediately obvious, but so I'm going to line up with the top of the object, and I'm going to go through the virtual focal point. So I'm going to line up with the top of the object, and I'm going to go through the virtual focal point and strike the lens. And since it's geometric, if you go parallel to the principal axis, you go through the focal point. Well, if you go through the focal point, you are going to bounce. And so this is going to bounce off parallel to the principal axis. So I'm going to go something like this. Okay, and so there we go. All right, so I got a point here. You can see the point where these meet. This is going to tell me information about my image. My image, well, the top of my image is here. Just like before, the bottom of my image is going to be on the principal axis. So we're going to just fill in the blanks here, and we get an image that looks like this. And so what do we notice about our image? Okay, well, first thing we'll notice is that it is definitely inverted. Okay, there's no doubt about that. And the second thing to notice is that these rays actually met where that image forms. So this is going to form a real image. I could take a screen and I could start with an object on one side and I could project the image of that object onto a screen on the other side. And if I put it in just the right location, I would get a really nice resolved image. I could see it very clearly. Okay, now in terms of the size of the image, like we saw with mirrors, that's going to depend, right? If you kind of jump back to this animation here, you can see the closer I get to F, the object is bigger. The further away I go, it's smaller. If I was exactly 2F, it would be the same size. I don't think we need to memorize that, but just have a sense that as long as you can see why it's definitely going to be inverted and it's definitely going to be real, those are the kind of the two key points. Now let's take a look at what happens when we go within F, within the focal length F. So still, again, we've got a converging lens, and so I'm just gonna draw this line. I find this quite helpful right down the center, so in case I miss. And then again, I'm just gonna pick some distance. It doesn't really matter distance you choose, and I'm just gonna draw the same distance on either side lens. And so I've got my focal point is there, and then over here on the other side, I've got my kind of my virtual focal point, and those are the same distances apart, so I'll call that F prime. And now I want to put an object within that focal length. So I'm just going to stick with the arrow this time because it's tried and true. I can only mess it up so badly. And there it is. It's vaguely arrow-ish. Okay, well, let's think about what we can do. Well, just like we did before, we can draw our first line, our first ray of light, I should say, is going to go parallel to the principal axis. So starting from the top of the object here, and then traveling this way, I go parallel to the principal axis, and that ray is going to bounce through the focal point, kind of like that. Okay, very nice. Now, the second ray gets a little tricky because you can see that I can't line up a ray that's going to go through the virtual focal point and actually go through the lens. But I can just put my ruler down in such a way that it lines up with the virtual focal point, lines up with the top of my arrow, and then goes towards the lens. And that's what I'm gonna do. So I got my ruler lined up here with the top of the arrow, and it's lined up with the virtual focal point, but it's obviously it's going to go and hit the lens because, well, that's what lenses are for. And so because it was lined up with the virtual focal point, when it refracts to the lens, it's going to go through parallel to the principal axis along like that. Very nice. And we see that they never ever come together ever, which is fine because while these actual rays don't actually converge, we know what to do in this case. We need to carry the refracted rays back and see where the lines that they represent actually converge. So I'll do this most recent one. I'm going to take this refracted ray and just kind of do a dotted line back here and see if that's going to line up with this first refracted line, which kind of looks like, I don't know, something like that. So right where they converge, we got the top of our image lining up here and the bottom of our image just below it. And so if we just kind of fill in the blanks, we can kind of fill in our arrow, and it looks like this, doesn't it? Okay. So what do we notice? Two things we can spot right away. Our image is, number one, it is upright. And number two, it is virtual. Okay, this image could not be projected on a screen because those rays don't actually meet. But of course, you can see this image. Like, this is how a magnifying glass works. You put a magnifying glass really close to the object and it looks really, really big. So last example here is going to be for a diverging lens. Now, a diverging lens, of course, does not have a real focal point. So let's jump over to this example here. Let's look at a diverging lens. You can see that when I have rays of light, maybe I'll do this one here, rays of light that go through the diverging lens, well, they're going to diverge. It's not just a clever name. And so these rays kind of spread out. And so kind of like we saw with mirrors, this is kind of similar to a diverging mirror, right? Like a convex or diverging mirror, in that no matter where I put the object, I'm always getting this this virtual and smaller image, and always upright. So we're just going to do one example here. So again, we'll do the same as before, where I'll just draw this line down the middle to kind of keep myself organized, and I'm going to put a focal point on this side right there. And I mean, these focal points it's all virtual, right? Like there's no real focal point because it's not really focusing. It's a diverging mirror. So I'll take an object. Okay, I've got my lovely arrow. Not feeling too creative today. Okay. Good enough. My arrows are getting worse as I go. That's fine. Okay, so what are we going to do? Okay, so my first ray is going to go parallel to the principal axis and strike the lens like this. Now, this is obviously going to diverge. It's going to go through the lens and it's going to diverge upwards. But where upwards is it going to go? That's a great question, I hear you asking. Well, it's going to diverge, it's going to bend upwards, but in such a way that it's going to line up with the virtual focal point on the same side of the lens. So I'm going to line my ruler up with this virtual focal point, line it up with the point of the lens where it hits, and I'm going to have my ray diverge up this way. So there's my divergent ray. Now, second ray that I'm going to draw is going to go, and I'm going to aim for the focal point, but I'm going to aim for the focal point on the other side of the mirror. So I'm going to line my ruler up with the top of my object and line it up with the focal point, the virtual focal point on the other side of the lens. I think I said mirror just now, but it's going to look something like this. You can see if that lens wasn't in the way, this green line would have continued through here and hit that other virtual focal point on the side, which means when it bends, when it diverges, it's going to bend kind of up, but not just kind of up, it's going to bend parallel like this. And again, now I've got my two refracted rays, so I can work backwards to figure out what my image is going to look like. Well, I'll carry this first refracted ray behind the lens because we got a diverging situation, okay, kind of like that. And then I'm going to go to my other refracted ray, and I'm going to carry this behind the lens, and so it goes, yep, something like this. Very nice. And you can see the point where they meet is where my image is going to form. So the top of my image is right here, the bottom of my image is right there, and I fill in the blanks, and away we go. So again, this is not going to matter wherever you put your object for a diverging mirror. There's going to be two results. One, it's going to be upright, and two, it's going to be virtual. And also, it's always going to be smaller. The image will always be smaller, as you can kind of imagine we've seen here. Okay, so a couple of things about lenses now that we can draw the diagram. So let's just stop and think for a second. Why do these lenses create the results that we see? So why is a converging lens a converging lens? And why is a diverging lens a diverging lens? Well, imagine if a ray of light comes along here and hits this first. And again, this is my converging lens. So if a ray of light was kind of going parallel to the principal axis, let's say, so it's just going along like this. Well, when it strikes the surface, because of the curvature of the lens, the normal is not in the same direction as that plane of light. The normal has bent around because of the curve. So my normal line kind of looks like this, right? And so as this goes through from air into glass or whatever the lens is made of, this ray is going to bend towards the normal. So I'm going to kind of bend this way a bit, right? So I'm bending towards the normal. Well, I then go from glass into air. And so what does the normal look like on the other side? Well, again, because of the curvature of the material, the normal might look something like that. And as I go from more dense to less dense, I'm going to bend away from the normal. So I'm going to bend kind of down this way. and away you go. So you can see that the bending of light, the refraction through a lens, actually happens in both locations, but the net result is that it kind of, in this case, it converges, right? You can imagine another ray coming from the bottom and the same thing would happen. Well, a diverging lens is going to work in the same principle. If I've got a ray that's kind of going towards the diverging lens like this, parallel to my principal axis, my normal is going to kind of be this way, isn't it? Right? Because of the curvature. And so this is going to bend, this ray is going to bend towards the normal a little bit. Okay, so you bent towards the normal, and then you hit the other side, and now the normal is kind of like this. Okay, maybe the normal is kind of like that. And again, you're going to bend away from the normal. So now you're going to bend even more. And so we get this overall kind of bending away. And so we get a diverging. So this is how lenses actually work. But it's important to recognize that since they bend in two places, that this can actually get a little bit complicated. There's two things about lenses that can make them not work so well. So the first limitation of lenses is that if we want light to bend a really precise amount, that can be challenging because remember, different colors of light, different wavelengths of light will refract by different amounts when they go into a new material. So you can get something called a chromatic aberration where different colors are bending more or less. The other thing is that it bends in two locations, right? It bends on the way in and bends on the way out. So that makes life a little bit more complicated. So we simplify this by assuming that the lenses are very, very thin. If the lenses are very thin, then we think about the bend as happening just in one spot. And we know it's not 100% correct, but instead of it going in and jogging across the lens, we imagine that it's happening in one location. And again, this assumption is fine as long as the lens is fairly thin. In fact, it gets to the point where we can actually reuse one of the formulas we learned about mirrors. So the mirror equation actually becomes the thin lens equation if we're talking about thin lenses. That equation was 1 over SO, the object distance, plus 1 over SI, the image distance, equals 1 over F, the focal length. And we can also talk about magnification, where the magnification of the object is going to be HI over HO, which is also equal to negative SI over SO. And again, the magnification just tells us like the ratio, the factor by which the size of the image increases or decreases. So a reminder of these conventions, and so some of these are going to be the exact same as it was for mirrors, but there's one extra that we have to keep in mind. So we're just going to rerun through them again to make sure we don't forget them. Okay, so the height of the image, HI, is going to be considered positive if it is upright. Okay, so if we create an image and it's upright, that is a positive height, and it's going to be negative if it is inverted. And by that we mean relative to, of course, the height of the object, HO, which we're just going to always assume is positive. And so for a given distance, an image distance, which is SI, it is considered positive if the image is real, and negative if the image is virtual. And so when we're thinking about these things, it's really important that we use the term virtual and real as opposed to like in front of the mirror or in front of the lens, because for lenses and mirrors, those things are reversed. A converging mirror will put a real image in front of it, but a converging lens will put a real image behind it because of the nature of how these things work. So keep in mind real and virtual. Now the last thing here is about focal length. The focal length is going to be positive for converging lenses and negative for diverging lenses. And that hopefully sort of makes sense because the converging lens has a real focal point, so we'll call that positive, and the diverging lens only has virtual focal points, and so that will be negative. Okay, so we're going to do two examples here. And for each of them, I think it's really useful to just sketch out a picture. It doesn't have to be perfect by any stretch. It doesn't have to be to scale. But at least if you have a rough sketch, then you know if you're anywhere close to a realistic answer. So I'm going to draw my just my principal axis. And I've got a 10 centimeter tall object placed 18 centimeters in front of a converging lens with a focal length of 12 centimeters. So I've got a converging lens. Now the focal length is 12 centimeters. So again, I'm not going to measure this out perfectly, but if I'll say 12 centimeters is approximately there, and then make that the same distance on the back side. And I place the object 18 centimeters in front of the the lens. So if that's 12, then 18 might be something like this, okay? And so I'm just going to include here a few dimensions. I've got there's my focal length there, which is 12 centimeters. I've got, that's F, and then I've got the height of the object is 10 centimeters tall. And then my height, or sorry, my object distance, my SO, is going to be 18 centimeters. And again, we're just kind of sketching this out to get a rough idea of what it's going to look like. So I'm going to draw a few rays and see how they behave. The first ray is going to be parallel to the principal axis. So something sort of like this. It's then going to bounce through my focal point on the other side, out the other side. And again, we're just sketching it out here. Then my second ray is going to go through the focal point until it hits the mirror, and then it's going to come through the other side and travel along like this. And so I can get an idea that my image is going to look something, it's going to look something like that on the other side. Okay, rough idea. Okay, so let's see what the thin lens equation says about things. 1 over SO plus 1 over SI equals 1 over F. Okay, so I'm looking for the image distance. So 1 over SI equals 1 over F minus 1 over SO. So my focal length, 1 over 12 minus 1 over 18 is my object distance. So this is like 3 over 36 minus 2 over 36, which gives me 1 over 36, which means my image distance is, well, it's 36 centimeters, right? Okay, not too bad. And again, that kind of jives with the picture there, right? Like it looks like it's further behind the lens than it was in front. The object was in front. Okay, so next up I can find my magnification. So magnification is just the ratio of the distances, or the negative of the ratio of SI over SO. And so that is negative 36 over 18, so that gives me negative 2. And again, that's not a big surprise because negative, so it's inverted. And then 2, it's twice as large, twice the height, which I can kind of see that in my picture. And so then I want to find my my image height. So since magnification also equals image height over object height, then image height is magnification times object height. And so basically I'm just going to double my image height, and so I get negative 20 centimeters. And the negative again just refers to it being virtual. Okay, let's take a look at one last example here. Now this is for a diverging lens, so we'll just sketch it out first and see what it looks like. Okay, so a diverging lens, which is going to kind of look, I don't know, vaguely this way. Very nice. And I'll just draw my line down the middle. Okay, it is a 4 centimeter tall object placed 8 centimeters in front of a diverging lens with a focal length of 10 centimeters. Find the location and height of the image as well as the magnification. So again, I'll make the focal length, I'll just pick some distance here and measure it out. So there's my focal length on that side, and it's gonna be the same on the other side. Okay, and so there's my kind of my virtual focal points, but they're both virtual, aren't they? And then I'm gonna put it 8 centimeters in front. So my object is going to be an arrow here. Okay, so maybe that's about 8 centimeters-ish. Okay, so there's my object distance is 8 centimeters. And then the height, you can see there that object height is 4 centimeters. And my focal length, I said, was 10 centimeters. Except it's not 10 centimeters, is it? No, it's not, because this is a diverging lens. So my focal length is negative 10 centimeters because it's diverging. Okay, so again, we're going to draw just a few arrows, a few rays, see what it looks like, make some guesses. And so my first ray is going to go parallel to the principal axis, and this is going to diverge up and away in such a way that it lines up with the focal point on the other side. This is going to diverge upwards and away in such a way that it lines up with the focal point on the other side. Now, the second ray I'm going to draw is going to be kind of aiming for it gets gunning for that focal point on the other side, but it doesn't hit it because strikes the lens, and then it bends parallel to the principal axis this way. Well, of course, I need to carry these rays back behind the mirror to see where they actually converge, because they don't actually converge in real life, and so we get something like this. And you can see that my image is, well, it's about here. It's in about that spot. It's small, it's upright, and so I kind of imagine a few things about few properties about it from there. So let's check the lens maker's equation. So first thing, 1 over the object distance plus 1 over the image distance equals 1 over the focal length. Okay, and so again, I want to know about the image. So 1 over SI equals 1 over F minus 1 over SO. So the focal length, remember, is negative. So this is 1 over negative 10 minus 1 over 8. Which gives me, let's see here, this is like 8 over negative 8 over 80 minus 10 over 80, which gives me negative 18 over 80, which when I invert that back over, my object distance is going to be about negative 4.4 centimeters. Okay, now taking a look at that picture, yeah, that seems about right. Like, it's smaller than 8 for sure, and it's definitely negative because it's virtual, and so that makes sense. All right, my magnification next up. So magnification is going to equal the image distance divided by the object distance, but negative. And so I'm going to get negative of negative 4.4 over 8. And I get a magnification of right around 0.55. And that number makes sense to me because the magnification should be less than 1 because my image should be small. And then last but not least, I can calculate my my image height, because that's just the magnification times the object height. And so a magnification of 0.55 times a height of 4 centimeters gives me an image height of about 2.2 centimeters at the end of the day. And it's positive, meaning it's upright, and it's smaller than 4, so that all kind of jives with what I expected. All right, that is it for our lesson on lenses.